Okay, so here's what we were doing last time. We were asking a subtle question given a curve, right? So we've got a curve here, such as, for example, that. And we were asking, given a point, and now we only want to consider a question locally. So I'm not going to look at the whole curve. I'm just going to look just nearby the point in question. And I want to ask locally nearby that point in question, can I view, let's say, for example, y as being a function of x? And at this point, yeah, right. And at this point, yeah, cool. In fact, at most of the points on this curve, it's fine. No problem. This locally business allows us to ignore most of the curve that would have been a problem, right? But there are certain points where the answer, even locally, is still no. And for example, this point, right? It doesn't matter how small, how restrictive, how locally you require your attention to be focused. Such a curve is always going to fail the vertical line test, right? You're just, that point is, the curve is just not good there. So at that point, if I were interested in, I don't know, the slope of the tangent line, or if I wanted to do, I don't know, linear approximations of something that's happening along that curve, and I wanted to be able to talk about y being a function of x, well, not there you can't, because it isn't. Right? It's not that the derivative is infinity or something like that. Absolutely not. There is no derivative because it's not a function. Right? So it's a nasty little problem. So we talked about that last time. Now we're going to talk about how to actually arbitrate that question. And here's the big idea. And this is I'm not going to get rigorous about this, but I do want you to have a good intuition for what's really going on behind the argument, and that is like this. Here's what a problem looks like. I wanted to be in the highlighter mode, sorry. Here is what a problem looks like. A problem comes about if the curve is at that very moment in the process of wrapping under itself. That's what's going to make you fail the vertical line test, is that fact that it's wrapping under itself. Well, if that happens, then you have a vertical tangent line, in which case you have a gradient that is horizontal, because gradients are perpendicular to level sets. And let's not forget what a gradient is, keeping in mind that a gradient is partial of f with respect to x, partial of f with respect to y. If that's horizontal, horizontal would mean that is 0. Right? The what you might call the vertical component would have to be 0 if you want it to be purely horizontal. Is everybody on board? Now, what we've written down here, if you have a problem, then this specific partial derivative will be 0. This observation by itself is not actually a good tool for our question, because this statement that we have here presumes that we know the answer to the question of whether there is or is not a problem. That's not helpful. But its contrapositive very conveniently turns things around, right? And as y'all recall, I'm a big fan. It's just super handy to be able to rephrase statements as they're contrapositive sometimes. So the contrapositive gives you an algebraic test. If you take this partial and it's not 0, well, then there's no way that this story up here is happening, which means no problem. Is everybody happy? Okay. All right. So, case could be made. What we've got here and what we were looking at on the previous page is kind of all single variable. I mean, look at the question itself. I want to view y as a function of x. I mean, that's a single variable function. And in fact, y'all probably have seen in your single variable calculus classes something that they would call implicit differentiation. Right? So case could be made this is kind of single variable. Now, you won't see these discussions here in a single variable class because it involves the gradient and partial derivatives, and that's not a thing for single variable, right? But nevertheless, it addresses what could be viewed as a single variable question. We are now going to push on and try to apply these same ideas to a unavoidably multivariable question. So I'm going to look at an equation involving 3 variables, which you'll notice gives me a surface in a 3-dimensional space, right? And now I want to ask the question, can I, locally at least, can I view one of those variables as being a function of the others? So totally analogous question. All right, and well, the answer is most of the time, most of the time. Vast majority of cases, in fact. And you can even see that in action. Let's suppose that I'm looking at a point, let's say way over here, and I want to locally, of course, means I'm going to consider all my attention just in that general vicinity. And in that general vicinity, what does the surface look like? The surface is just going to be kind of just, about like this. It's going to be a little kind of vaguely disc-like thing. And does that pass the vertical line test? Yeah, it's fine. No problem. And it's going to work just fine there, and it's going to work just fine at even down here, most of the points on this surface. Yeah, it's cool, no problem. Yes?
So how does it not fail? Because there would be like the sheet below it too, right?
Well, but again, locally, right? So locally means that I'm only interested in stuff that's going on within the little yellow bubble, right? And I get to choose how small to make the yellow bubble, and I choose to make it small enough that it doesn't touch anything down there. Yeah, is that cool? Yeah. Okay, so where is this going to fail? And it's going to fail at points that are, I'm going to say, morally equivalent to where this failed. At points where it's at that very point, that's the instant that it is starting to actually wrap under itself. That's the problem. That's what could go wrong. And as you see in the picture here, let's get rid of that, clean that up. If the curve is in the process of wrapping under itself at that point, well, I appeal to your geometric intuition. If it's wrapping under itself, then the tangent plane would have to be vertical. That's how you wrap under, right? I mean, under, you see what I'm saying there. Well, now wait a second. If it's a vertical tangent plane, then that would mean that the gradient would be horizontal. And what does horizontal mean? Well, horizontal means that the third component would be 0. And so we have this same situation. If you have a problem, then there's an algebraic giveaway, and that is that z partial would have to be 0. So contrapositive, just like before, partial not 0, no problem. And that is our implicit function theorem. And again, I'm not treating this rigorously at all. This is just sort of intuition purposes, right? But this leads us to, our intuition tracks with this, strict statement of the implicit function theorem. Now, one thing I want you to notice in particular, this example that we just talked about. Let me clean this up. When I was asking a question about whether I can view z as being a function, notice I needed to take the partial with respect to z. Back here in the single variable example, let's see, here it is. Yeah, in the single variable, and let me clean up this mess. When I wanted to view y as being a function, I needed to take the partial with respect to y. That pattern holds. And you can consider various different sort of alternative versions of this kind of thing, be they 2-dimensional or 3-dimensional, and the pattern will always hold. And as I have written here, whichever variable that you want to view as a function, that's the variable that you take the partial with respect to. Very handy, convenient way to sort of remember the rule. So here I want to view x sub I locally as being a function of the others. Cool. Take the partial with respect to x sub I. And as we saw in these previous two cases, the actual test then is if it's not 0, then yes, you can view it locally as being a function. Yeah.
So I guess, like, what does that actually mean? Like, what is, when we say we can take x locally as a function of the other variables?
Yeah, that means such as what we saw here. Like if I wanted to, let's suppose I wanted to look at this, in the hang on. I wanted to look in this general vicinity here, right? And which means that I could not care less about anything going on up there or over here, right? And I ask just along this little piece of curve right there. Let's talk about dy dx. And dy dx is something that I can talk about here because I'm taking the derivative of this thing called y, which is a function of x. And you can see in the picture here, yes, locally, ignoring all this garbage, locally, y is a function of x, so feel free to talk about its derivative, right? But on the other hand, if I were at this point, right, and then someone said, hey, so here's the thing about dy dx at that point, blah, 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 then you should shoot your hand up and say, I don't know what you're talking about. You can't say dy dx at this point. Y isn't a function, not even locally. You can't take derivatives of curves. You can't take derivatives of any other object, functions only, right? And y is not a function here in any sense, and so derivative of it is just garbage talk. Is that satisfying?
Yeah. Okay.
Yeah. Okay. Yeah. So, I mean, to be fair, it is. I know it's kind of a mathematical formality, but I mean, the math is really ultimately all about deductive reasoning, where we take known, established, true statements and conclude subsequent true statements. And writing down garbage accidentally is not part of the plan, right? So we got to make sure stuff makes sense before we write it down. Yeah. The what now?
The bubble.
Oh, the locally? Yeah, it's you get to make it as small as you want to make it.
How do you write that out?
Yes. Look, great question. But what you're asking me is to go into some rigors that would make a lot more sense in Math 431 than they would in Math 219. And look, it's wonderful, and I'm all for it, but I just can't. Yeah, in this context. Yeah. Okay. So, yes.
So would the same idea apply if the output is more than one variable, like if it's R and it's R?
That's a really good question, and that's another sort of that's a more sophisticated question. I think that may be actually more of a Math 531 kind of thing. Okay. Anyone want to go for a 600 level? No, all great questions, but it's just not what we're going to be in Math 219. We're going to be looking only at single equations. Namely, where the output is just real valued only. Yeah. But very natural question. Yeah. Okay. All right. So let's see here. We have our new tool. Let's make use of it. Here is a reasonable question that someone might ask. You might be doing, I don't know, some economics maybe, and you write down an equation that looks something like that or something, right? And then you want to talk about the derivative of x with respect to something, but you can't because x is not yet known to be a function. And again, you can't take a derivative of anything but a function. It doesn't make any sense at all, right? So before we go around asking questions about what the derivative of x is with respect to whatever, can I even ask that question because I have to first establish that x is a function. So how do we establish whether x is a function? I take the partial with respect to x. This is the function whose level set I'm looking at, so that is the function that I take the partial of. All right? So the partial of the function whose level set you're looking at, the partial with respect to the one that you want to be a function. Everybody on board? That's our rule. Handy dandy rule. Let's see here. Yeah, there we go. So yeah, you take the partial derivative, you get that. Now we're interested in what's going on at this point, 1, 2, 3. So that's the point that I plug in. Right? We plug in x equals 1, y equals 2, z equals 3, and some arithmetic ensues. And what we find is that this partial at the given point has value 4, which is not 0, and so yes, we're good. It's all fine. X is, locally at least, a function of y and z. And what's wonderful about this is notice I never solved for x. I don't think I could solve for x. It's a cubic, right? That's kind of prohibitive. I think technically it can be done, but it's, in practice, not really. Is everybody good? All right. Now, a harder question comes up next, which is, okay, fine, cool. So x is a function. Great, x is a function of y and z. Now I can talk about the partials of x with respect to y and z. How do you do that? How do you actually compute these partials of our newly established function? And, oh my God, am I going to have to solve for x and then take partials of it? Wouldn't that be a bummer? That would kind of defeat the whole purpose here. So there is a really clever way around this that involves the chain rule. And here is a discussion of what you might call a more complete discussion than what I'm actually going to show you. Now, if you want to see the more complete version, there it is, and I clean up the crime that I'm about to commit here. But I'm going to encourage you all to go with this, what I'm calling the alternate diagram. And this is, again, a little bit of a math crime. Y'all will recall I made a big deal when we were talking about the chain rule that you can't just apply the chain rule to any old diagram. You feel like the diagram's got to follow certain rules. It's got to actually be a composition of actual functions. And that's weird looking, especially because of that arrow there. This seems like it's violating my own rule. And it is. And so, again, granted, and, apologies. There is a cleaned up version. Here it is. And look, this isn't violating anything. This is clearly a composition of two functions. No problem. And if you want to wade through the details in this more sort of, appropriate form, you can, and it's fine. But in practice, this gives you everything that you need. And let me just kind of talk through it. I think you'll find that this is believable. We've got f being a function of all these variables. Whatever equation comes to us is some function equals a constant. And we've just established, let's presume, that one of these variables can be viewed as a function of the others. And I'm going to kind of circle like this and do kind of like that. I know it's weird to think of one variable in a list as being a function of the others, but let's just, it's kind of like that. So now, question, as xj changes, that's one of our other variables, how does xi change as a result? So I want to compute the partial of xi with respect to xj. And this is kind of a general version of the question that we find ourselves looking at. We've newly established that this is a function. I want to take its partial with respect to one of the input variables. That would look like this on that diagram. So, and now I'm going to play fast and loose with diagrams like I warned y'all against, like I warned you not to do, right? But again, you can clean it up if you'd like. It's fine. But I'm going to do it in the convenient sort of fast and loose way. Here's the partial derivative that we want to compute, and you notice it's just kind of what's going on with that arrow. And it's part of this path which contributes to the overall amount that capital F changes. And you can see right here, it's sort of the first step along that path, and then the second step, let's see here, different color. Okay, I'll use yellow. How about that? Second step is that factor right there. Okay. So that's the first path along which xj changes can propagate. And then, don't forget now, there's also this other, you might say, sort of direct path along which xj changes will just directly contribute to changes in f. And these are the two paths, and grand total, they give you this total amount of, the derivative of f as xj changes. But wait a second, f, of course, is a constant. It's not allowed to change. If it's not allowed to change, that total derivative has to be 0. Everybody cool? All right. Cool. So, great. We were interested in solving for that specific partial, and look how easy it is to solve for it. You just move around the one term, divide by the other term, and bam, there's your formula. If you want to compute a partial of your newly established function variable with respect to one of the others, formula. Boom. Yes.
Why are we saying that the input variables are dependent on each other?
The input what now?
Like the input variables depend on each other. Like.
Well, see, because that's what we, for example, established in such as in this example right here. It starts off that x, y, and z are variables. They're all independent variables. They can kind of be whatever. But I've established that if I confine myself to the curve or surface that this describes, locally I can treat x as being a function. I mean, I could, right? And I don't even have to actually solve for it. But if it's going to be treated as a function, then I need to be able to talk about how to take derivatives of it. And I'm saying that this is how you would take a derivative of it. Yeah. Yes.
Why do we set f equal to 0 at the beginning?
Well, we're not. You mean at the very beginning, like back here?
Yeah.
Okay. So the reason I need this, it's a great question. I need this to be set equal to a constant because I need to be able to, at this point in the argument, I need to be able to argue that the gradient is perpendicular to it, and gradients are only perpendicular to level sets in particular. Yeah. So that's why it's got to be a level set. That's why it's got to be stuff equals constant. Yeah. Okay. So we've got ourselves a formula. Now there is a landmine that I want to help y'all to avoid stepping on. Here is a really easy mistake to make. Lots of students step on this landmine, so I'm gonna do my best here. The landmine is this minus sign right here. That minus sign, very important. I encourage you to write that minus sign down first. Right? Don't think to yourself, I'm going to think about what all the rest of this means and work out some partials, and then I'll remember to throw in that minus sign later. No, get that minus sign down on the page immediately. And here's why. If you forget it, you got to keep in mind, I'm explaining this from the point of view of students taking a test, which is going to be graded, and how are the graders, aka me, how's the grader going to look at this, right? If you forget the minus sign, let me scratch it off, hypothetically. Right. Get rid of that minus sign. And if you were to just write down that this is just equal to that, first of all, it's wrong. But worse, it looks like the student wrote this down based on the following rationale. Hey, check it out. There's a partial f. I'm going to cancel both of those. And the denominator of my denominator becomes my numerator. And the denominator of my numerator is my denominator. And hey, check it out, it just worked. Right? So This, of course, is all nonsense. The notation's very, very unfortunate, but these things here that look to be fractions, they're not really. They're not fractions of independently well-defined, unambiguous things. They aren't. Right? Partial f is not a thing. At least it's not a single thing. Right? Partial f in the top represents some scenario where we're assuming certain things about which variables are constant and which variables are changing, blah, blah, blah. This other partial f is representing how much f changes in a totally different scenario. They are not the same. They do not cancel. This is all nonsense. Right? So that's why the minus sign is so important. This minus sign, this one little minus sign, is the only thing that distinguishes a perfectly valid equation from something that looks like what a student would make up if they didn't know what was going on. Everybody see that? And it's just a dangerous little reality, right? So I don't want y'all stepping on that minus. I don't want y'all to write down something that makes it look bad. Right? I want it to look good when y'all write stuff down. So that minus sign, super important. This is what makes your work look like you know what you're doing. That's where points come from, of course. So make sure to keep that in mind. Does that make sense? Is everybody good with that? Okay, so let's see one. You'll recall we've already looked at this surface. We've already established that x is locally a function of y and z, right? We did that in the previous example. We know x is locally a function. Therefore, it is reasonable to talk about what its partials might be. How would I compute, now that I have that x is a function, how would I compute its partial with respect to, let's say, z? Okay, well, what we would do is first write down the formula from the previous page. Now, let me talk about how I got that. This is not technically exactly this formula from the previous page. The formula on the previous page assumed that my variables went by one collection of names, and this application here, the variables are totally different names, right? And by the way, that's just always the case. So how did I get it? And there's sort of a two-step process, and that goes like this. Step one, minus sign. Please, I emphasize, write down the minus sign first. In fact, I speculate, and I make no promises, but I speculate that if a student were to write down partial x with respect to z equals minus sign, and then time gets called, and that's it, I think that minus sign alone would probably get a point, right? It shows the student remembered something, and so that's worth something. So write that down first, right? So that was step one. And then step two was to realize back here that, again, this nonsensical garbage argument that the numerator is the denominator of the denominator and all this business here, well, it's garbage and it's wrong, but it does produce the rest of the formula very conveniently, right? And it's a nice little memory tool. Even if it's garbage, it is a nice little memory tool. And so I encourage thinking of it in those terms. So just like I did on the previous page, that goes there, and that goes there. And that tells me I need to compute that partial, which is easy. And I need to compute, I need to compute that partial, which is easy. And now plug in some numbers and bam. Everybody good? All right, don't forget the minus sign. Okay. All right. All right, the last thing I'm going to say about this, and then we're going to move on to chapter 3. I broke up here what I would consider really one question, and I broke it up into two separate examples. And I want to recognize that that's not how problems tend to come at you in the real world. In the real world, and therefore also to the extent I can, on my exams typically, and feel free to look back through my old exams. at a bazillion examples of where there are questions that are kind of like this. The question will not just come straight out and tell you free information that one of the variables is known to be a function of the others. That's just not how stuff comes at you in practice. In practice, what happens is there's some surface you're looking at, so some equation you're looking at, and you know that you're interested in what's going on near some point, and you find yourself wanting to be able to compute a certain partial derivative. Maybe because you already know what you plan to do with that partial derivative, if you could, or maybe because somebody just directly asked you and said, hey, I sure would like to know that partial derivative. Can you help me? Right? And so what you've got to do is you've got to recognize, and this is part of your responsibility as students in this class, to recognize that there's really two things to be done there. If you want to compute a partial derivative of something, you can't just start writing down formulas. What if that thing isn't even a function? Right? So step one, the very first thing you've got to do in such a case is you have to actually address the first question. You've actually got to say, hey, is this actually a function? And you've got to address that appropriately. So here you go. Here, this is part one. Part one is to establish that the thing you want to take a derivative of is actually a function. Step two, after having done step one, with step one done, then step two here is to compute the partial you've been asked, as we did here. All right, so heads up about that. That's sort of the observation that I have right here. Don't forget to check whether it is specifically that the relevant variable is locally a function of the other variables. Okay. By the way, on my grading rubrics, typically questions of this sort, and so again, if you were to see a question like this, establishing that x is actually a function of y and z would typically be about half of the points for the question, and then the computation of the partial would be approximately the other half of the points for the question. So again, really big deal. It's kind of a landmine, right? I mean, if you just kind of naively just dive into a calculation as if that makes sense, you just missed out on half of the points. So again, don't do that to yourself, right? Make sure you get those points. Is everybody on board? Is everybody? Yeah. Okay. Cool. On to chapter 3. So you may recall we did 3.1 a while ago. 3.1 was I feel a very handy tool to have to take a very handy point of view on the chain rule. So we did 3.1 already. Diving in now to 3.2 about arc length. This is a section that has a combination of topics in it, some of which are really, really important in this course and that we're going to be using a lot of, and some of which is kind of, useful for sort of rigor purposes that don't really have that much bearing on what we're going to do in this course. So I'm going to spend a bunch of time talking about this stuff thoroughly because this is really important, and then the rest of 3.2 I'm going to go through pretty quickly. And there's some things that have to get said, but it's not really certainly not as important. Okay, so here we go. Starting off. How do I compute the length of a parametric curve? So suppose you have a curve like this, parameterized by whatever formulas. How do I compute that total length? Real quick, the whole is the sum of the parts. Right? That's how integrals work. We're going to talk a lot more about that when we get into chapter 5. But the whole is the sum of the parts. If you want to know the total length of the curve, well, you're going to look at each little piece of curve. And you're going to add up those individual lengths over the whole curve and get the total length. That's the strategy. Okay. So what that means is, before we do any of that, we've got to figure out what is then this length of a little piece of curve. How am I going to get my sort of hands on that length ds? So the first foot in the door on that is a particular vector here called dx, sometimes called the position differential. You can think of it as being a displacement differential. The idea of dx is, given that I'm at a certain point on the curve, dx says, what is my linear estimate of how much position x changes? That's what a differential is, right? Remember, a differential is a linear estimate of a change. So x is position, dx represents an estimate of the change in position, otherwise known as a displacement. Okay, so easy formulas for how to write down dx. It's the displacement, and that's one of the key ingredients that defines what velocity is. Displacement is velocity times time, right? So this is, you can think of this as being basic physics, or sort of a, in some sense, kind of a point of view in geometry. But displacement is velocity times time. Is just kind of a fundamental idea. Is everybody happy with that? Okay. All right. All right. So what is ds? Well, again, ds is representing, in some sense, our estimate of the length of that little piece of curve. Now, it's still an estimate. I'm going to highlight it on the picture here as being the length of that little piece of curve. Now, it isn't actually. ds, again, is just our linear estimate of that length, right? And so how would I make a linear estimate of that length? And well, look, we've already got a linear estimate of a displacement. The displacement really closely tracks that little piece of curve. Wouldn't it stand to reason that the linear estimate of the length of the curve would just be the length of the vector we're using to approximate that piece of curve? And so I claim ds is the magnitude of the dx vector. You buy it? Okay. All right. These are really important objects. We're going to be doing a ton of stuff with the dx vector and the ds scalar differential, length differential. One other thing that we're going to be doing a ton of stuff with is the unit tangent vector. It ends up being really useful in a lot of ways. So again, it's just a unit vector pointing in the direction the curve is going. Now, if you think about it, the direction that the curve is going, right, at that point, the direction the curve is going is the same direction as the direction that dx is going, which is the same direction that the direction that the velocity is going, x prime. Right? All those vectors point in the same direction. So dx, velocity, t is just a unit vector pointing in their direction. And we have a really easy formula for how to write down a unit vector that points in a particular direction. You want to find a unit vector, just take whatever the given vector is and divide by its own magnitude. So handy dandy formula for t. And yeah, let me pause on that for a second. Is everybody happy with that? Okay. Now, the next thing I want to say about it is that t is what allows me to write yet another version of dx. We've already seen that dx equals those things. I claim that dx is also equal to this thing. And there's two different ways to see this. One point of view is, I think, very intuitive, and I like students to have a good intuitive sort of point of view on things. Dx is a vector. It has a direction and a magnitude. This product has a direction and a magnitude. T being a unit vector, it represents the direction. ds represents the magnitude. Now, what direction is dx pointing? Well, dx is pointing in the same direction as t. What's the magnitude of dx? Oh, we saw that already. The magnitude of dx is ds. So really, this little bit of algebra I've written down here, t ds, this is the unit vector direction of dx. This is the magnitude of dx. Therefore, this product is the direction and magnitude of dx. So it's dx. Right? This product here looks like a duck and quacks like a duck. So it's a duck. Does that make sense? I think it's a really nice way to think about it, right? Vectors only have two features, direction and magnitude. This is the same as dx with both. So that's one point of view, and if you're happy with that, that's cool. Here's a different point of view. If you want to see something more algebraic, let's see here. T, we have that formula. ds, don't forget, we have that formula. Right, now let's look at that product now. T times ds. T times ds, let's see here. This times that. Notice the magnitude of v cancels. And I get left over, I have only v dt, which we've already established as dx. That's a different way to think about it. If you like, take your pick. They're both nice points of view. Okay. All right. This is the portion where I'm going to start moving more quickly because everything else is kind of just formulas and stuff that we don't have time to make a thing out of in 219 anyway. We've already agreed that the total arc length is integral of ds. We have established that ds is v dt. And so here's a final formula for how to compute arc length. Arc length is just the integral of the magnitude of the velocity vector, otherwise known as the integral of the speed. And easy plug and chug example here. You want to compute the length of a parametric curve. Okay, well again, formula. This is just exactly that formula. Let's see here. We need to compute the magnitude now. Now don't forget a magnitude is a square root of the sum of the squares. Magnitude of the velocity here I get from taking the derivative of the given parameterization. And you see how these components of the velocity are what I'm going to be putting under in doing the square root of the sum of the squares. And now I have an integral to compute, and this is not a very nice integral. But nevertheless, this is an integral that if I were to be able to compute this, and in practice, honestly, I'd have to do this numerically, right? This is one of these really unfriendly integrals. I certainly don't want to have to do that, but that is the integral that would give me the answer to the question. Now, why did I pick an example where it turned out to be ugly? Well, because, again, I wanted to be representative of how this stuff tends to go down. And you can imagine it's going to go down kind of like this most of the time. Because, after all, length is an integral of a magnitude. And a magnitude is a square root of a sum of squares. It just intrinsically is a square root of something ugly, right? And they just tend to be nasty like this. Okay. All right. Good news. I am never going to ask you to work out an integral of something that is unfriendly, right? So that you can view the ugliness as actually good news. That means that the fact that these tend to be ugly integrals means that most of the time you're not going to have to compute them. All right. Okay, next thing I want to talk about arc length parameterizations. First, I want to talk about the idea of a reparameterization. Here is a curve, and y'all will remember, of course, the graph parameterization. The idea of a reparameterization is that if you take the t and just set it equal to some expression involving some other parameter, and there are some conditions in here that we have to worry about. I don't want to get bogged down in that. That's not what Math219 is. But such as an example like this, if I just take this formula for t and just plug it into there, right, then I get now a new parameterization. And that new parameterization, just like the original one satisfies the equation, this new one does too. I have here two perfectly good parameterizations of the same curve. And you can plug in for yourself and see that if this is your formula for x, and if this is your formula for y, then y is equal to x squared. Okay, so the big idea here is that if you have a relationship between parameters, let's see here. If you have a relationship between parameters, you can plug that into one parameterization and create another one. So what we're going to do with that is use arc length, literally, as our new parameter. If I'm at a point on a curve, point on a parametric curve, I can think of that as being at a certain time t, where I'm thinking of t as being my parameter. But just as well, I could think of it instead as being defined by, well, it's the point where we're a certain distance away from a given starting point. And I'm going to point out, y'all have actually seen this, I think, in practice, mile markers on the highway. Right? So you can imagine as you drive along the highway, you are literally putting by your presence a position as a function of time, right? You are in a given location at any given time on the clock, and that traces out, parameterizes that path, that road, right? Well, mile markers do the same thing. It just doesn't involve you, right? Mile markers tell you where on the curve is, let's say, 175 miles from, downtown, whatever. Right? And then, okay, well, where is 176? Well, 1 mile further down the road. And they have these mile markers, every mile as you go down the highway. Those mile markers give position as a function of distance. Again, distance from some preset, maybe the state line or something like that. Okay. So, well, we have a formula for how to compute distance. Here's your formula for distance. Notice that distance is a function of, well, wherever you decide you want that stopping point to be, which I'm going to call t. So we've got distance as a function of time. And you've got to work out the integral, right, and see what this function is. But once you have distance as a function of time, then you have yourselves a new parameter. And you can take the formula for your new parameter, plug it into your existing parameterization, and out comes a new parameterization. And here we would have our new parameterization would give position as a function of distance, aka arc length parameterization. It has certain nice features. It's natural. It doesn't depend on you. It doesn't depend on how you choose to drive and whether you got a late start that morning and stuff like that, right? It's just intrinsic to the road. The mile markers are always there, right? Independent of anything. And certain other things that are really nice. But in practice, they're very hard to compute with. Here's an example, the purpose of which is just to show you how annoying it is to do this. And I went to some trouble to craft a parameterization which would cause this ugliness that we were afraid of, square root of the sum of the... Oh, whoops, I'm sorry, I had the wrong one. This one here, the square root of the sum of the squares, to actually work out nicely. And conveniently, it worked out to where I ended up with a square root of a perfect square, which makes the square root go away. Right? That was tricky to come up with such a special curve to where the integral actually turns out to be doable. And even then, it's still kind of a bummer because now I've got to solve for t, and I don't know how to solve cubics. Right? So in practice, arc length parameterizations, it's more trouble than it's worth. I do need you to be able to know how to do them, but that's really all we need it for. And so we'll draw the line right here for today. Y'all have a good day. See you on Friday.